This is the introduction to embedded systems. I am Van Pataluna, your instructor, and uh, the first chapter of this particular course would be for you to be introduced to embedded systems. But first of all, I would like to ask everybody um, to still remember your computer organization and architecture, about architecture and organization, because this particular chapter or unit, we are going to be dealing with architecture and organization. Um, Before we even dig deeper into embedded systems, let us review first the um, the background or the foundation of embedded systems, which is basically the microcomputer. Okay. Now, so I would like to get you all to um, think over the two questions, that perhaps that you're going, or the two things that you're going to be asking yourselves later. And that is computer organization and architecture. Okay. Now, the microcomputer, which is the foundation of embedded systems, is basically composed of these three components. And I don't think that this will be something new to you. This has been discussed over and over again in previous courses, but just a review that we have the following three devices. We have the CPU, memory, and of course your input and output systems. And without this, any of these three not present, that could not be, or that could not be a microcomputer. So it has to be these three. Now, how are these three related to each other is shown on the next slide, and that is basically the we have the input, we have the CPU, the output, and memory linked together by this particular figure here. Now that figure uh, is basically the architecture of a microcomputer, a modern microcomputer. So we have the CPU writing, reading data from memory, and of course input. The CPU gets input from from the input device, and of course CPU sends signals to the output device. Now, of course, it might not be true to all of the computer systems that we have right now, because we have also direct memory access and so on and so forth. But this is the foundation of it all. Okay. Now, if you remember to ask about architecture and organization, now let's try to differentiate these two. That's just a review. So you all know this has been defined already in CPU 314. Now, architecture is those attributes which is visible to the program. Anything that is that can be seen, or anything that can be, or it is tangible in this particular case. So, for example, so we have the instruction set. We have the number of bits, or how wide is the data bus. So we talk about 32-bit, 64-bit. So that's part of the architecture. Also, the I/O mechanisms and the methods of addressing. Um, it's basically part of the architecture of a particular computer system. Now, organization, on the other hand, is how are these features are implemented, such as, of course, the control signals, interfaces, the memory technology, and let's also how your instructions, okay, or how the instructions are being implemented. In this case, let's say, for example, multiplication. Now, some systems have a multiply instruction. Some architecture have multiply instructions, but some are not. But let's see in the architecture point of view. Okay, so where's the question? Is there a multiply instruction in the instruction set? Well, if there is, In the organization side, the question now is that how this multiplication instruction is being implemented, because it can be done two ways. First, it can be done by having a discrete multiplication hardware in the architecture, in the arithmetic and logic unit CPU, or it could be done by repeated addition. So we have both ways still performing a multiplication instruction. So this is the overview, okay, or say a quick a quick explanation of architecture and organization. Now, this is the granddaddy, you know, of all of the modern computer architecture, and I have to say that there are two persons that I have to give credit for, and except from God Almighty, these are my gods, and we call them von Neumann and of course Mr. Alan Turing. Now these two people, or two guys, these are computer scientists, and they come up with an idea of a stored program concept, because before programs are not stored. Programs are you know, in a punch card, and if you execute a program, you have to load a program, and of course the system or the computer does not store these programs and the system itself, but it has to be stored in a separate storage. And instead of having the memory only storing data, memory can be also be used to store the program, okay, or your code. And the ALU, for the first time, is not operating on binary data, because before the architectures are operating on a decimal system, okay. And the control unit interprets instructions from memory, and of course it executes the instruction, while your I/O equipment is operated also, is controlled by the control unit. And this particular architecture was developed by or at Princeton Institute of Advanced Studies at Princeton University, and the time when this was developed was in 1950s, just after World War II. So imagine that it's not that long ago that this, or it's not that, or shall I say, the architecture is very, very old. Okay, it's more than about, like, say, 60 years, 60, 70 years. But it was the foundation where the modern computer architecture was based. And this is the structure of the von Neumann machine. And when you see, as you can see, you have the input output equipment, of course, memory to the right, and in the middle we have the arithmetic and logic unit, or ALU, and program control unit. Now, my question to you is, in a modern computer architecture, okay, which of the following, which of in the figure constitutes the CPU? Okay, now you will going to be answering, of course, the arithmetic logic unit and program control unit. That should be the CPU. Yes, it's correct. At the time of the von Neumann of the foundation of the von Neumann machine, the ALU and program control unit does not constitute a unified system. So they are both separate systems. So now we put the ALU and program control unit into one block, one system, and we call that the CPU, or the central processing unit. Okay. Thus, going back to the second slide, so we have now the I/O, the memory, and the CPU, and the relationship between this system. Now, embedded systems, on the other hand, now let's go to embedded systems. It's basically a computer system that's designed to do a few or dedicated or specific functions, and attributed also of its very, very fast response, in which embedded systems is used in real-time systems. And the embedded system is controlled by one or more main processing cores. It's typically either a microcontroller or a DSP. Now, we talk about embedded systems being a computer with limited capabilities. Yes, it's true. It's because it has to perform only some dedicated tasks and does it with efficiency, and embedded systems is basically used in real-time systems, because it could deliver response with very little to zero delay. Okay, so anything that is doesn't have a delay, they we call it real time. Okay, so this is an example of an computer, but we'll talk about more about it later. Now, we want to reduce the confusion of an embedded system versus the system that we are very familiar, that everybody have used, and that's the personal computer. Okay, now it is wise to compare them because these two are the same von Neumann machine. These two are still a microcomputer system. Okay, so more or less they belong in that category. But what's the difference between these two? Now, embedded computer, okay, now it is implemented for a particular purpose, while a PC, it's multi-purpose. It can do a lot of stuff. It can do a lot of work in it. So, for example, like say checking email, surfing the web, listening to music, doing word processing, or perhaps like this, what I'm doing, like recording the screen and of course my voice. Okay. Now, in the let's look at what an embedded computer could do versus what a PC could do. So you have here on the left side, so you could all do those things, but an embedded computer could only just be like, say, for example, controlling the speed of DC motor. That's its job. Okay, but an embedded system, as I've said, could perform the control with very high efficiency because it only does the job. Now, of course, it applies also to human factors. Now, we humans are typically multitasking. We are programmed to do things, so we can do things uh, at one time. Okay, let's say we are talking as well as hearing things. Let's just do things that we are basically programmed to do. Now, because let's say for example, because we can do a lot of stuff all together, we are not doing that very efficiently. Okay, because we're doing a lot of stuff, we're doing a lot of things. But if you are just going to do one function, okay, you have all the time, all the resources, then you could do that function very efficiently. Right? Now, what are applications in embedded systems? I'm going to be showing you a few examples, but I want everybody to think of a particular example in embedded systems. I'm going to ask that later. I'm going to ask you to give you an example of an embedded system. Now, of course, we know already the definition of an embedded system. Now, think of an application where embedded systems is used. So, say for example, in household. So we have this digital timers and microwave ovens. So we have it in washing machines, in digital clocks and watches, and of course in automotive, which is very popular application in embedded systems, like for body control module, for the GPS, for the anti-lock brakes, and of course in communications. So we have modems, routers, network interface cards, and of course a very lucrative market for embedded systems and multimedia players. Okay. Now, let's say, for example, music players. Okay. Now, of course, you may be wondering why, uh, say in the case of cellular phones, right? Of course, the mobile phones right now can do more than just call and text. Could do also movies, surf the web, play music, and so on and so forth. Now, a mobile phone is an example of an embedded system, but of a different kind. Okay, it's a different kind of an embedded system because our embedded systems, by the way, that we're talking about here, would be implemented in a very simple device. Okay, and that is the microcontroller unit. I'm going to discuss more about the microcontroller unit later, this particular unit. Now, the cellular phone, of course, is an embedded system, but it's not the same. Right? It is not the same in our definition, right? Because we say embedded systems that it can do only a few tasks with great efficiency, right? So we are going to be focusing on that definition of an embedded system, not an embedded system that we find in the cellular phones, in the mobile phones, these multimedia players, multimedia devices. Okay. Now, an embedded system is attributed also in its key features, such as having an interface. Okay, so let's say, for example, if you want to interact with an embedded system, usually we find like displays, keyboards, and so on and so forth. But it's not entirely true, because embedded systems could function without human intervention. Embedded systems could function with just sensing its environment. That's it. That's input devices, and the output devices could be, let's say, for example, sending signals to other or say mechanical device. Okay, so it's free from any human intervention. Okay, so if you have to have it interface with humans, so you should have some human interface, such as what you see in the figure there. So you have a screen and some switches. Okay, so in general, an embedded system is a system built to perform its duty completely or partially independent of human intervention, and is designed to perform a few tasks in the most efficient way possible, and interacts with the physical elements such as temperature, let's say some mechanical devices, pressure, so on and so forth. Because embedded systems are used in this particular is used also to interpret, um, signals from the environment, temperature, pressure, and so on and so forth. So if you want to know a temperature, let's say for example your body temperature, and of course the signals, the temperature is basically an analog signal. If you are going to, it's not a discrete signal, so therefore you have to convert that from analog to digital, and of course the analog, the embedded system would now crunch the digital signals so that it could be readable to humans. Say, for example, a digital temperature is very popular right now. So, of course, if you're going to read the temperature, you are seeing a 7-segment display on an LCD or an LCD. So, it's an embedded system or embedded computers basically trying to reconstruct the data from the analog to digital converter so that we can read the temperature as digits, not bits. Okay. Now, in our definition of embedded system, we came in through a term, we call it real time. Now, real time systems, okay, it's one of the feature an embedded system could do. Not all computer systems could do real time, but embedded systems is basically a very good real time system platform. Okay. So embedded systems are, as I said, often required to provide real-time response. Why? Because of its dedicated task. So if you have a few tasks, then you can do your task very efficiently without delay as possible. Okay. Now in real-time systems, it is expected that the system performs with no delay. Okay, so you give an input to the embedded computer, and the response should be 0 or with less delay, or ideally no delay at all. Okay, for example, in aircraft systems, nuclear reactors, sensors, and so on and so forth. Now, of course, some of these systems are life and could cause and their life could result in a life and death situation. Therefore, response is very critical. Okay, and only embedded systems could do that. Okay, now, well, of course, embedded systems has its own history, so that's why you have to discuss some. I'll just go over to the history of the embedded system. Well, it's basically started with the Apollo guidance computer, which was developed at MIT. The Apollo is basically the moon program, the moon landing program of NASA. So, of course, the Cold War, thanks to the Russians and the Americans pointing missiles at each other, it also led to the development of a guidance computer called for the Minuteman missile. It's a ballistic missile with nuclear warhead, and it was released in 1961. And this particular computer is made out of transistor logic with a hard disk and a main memory. So typically, it is the start or it's the prototype of things to come, in a modern computer system. And the embedded system basically evolved from the microprocessor itself. We know the Intel 4004, the first microprocessor, provided a key system for much powerful computers to come. Okay, now the Intel 4004 is just a processor. Typically, it only have the CPU inside and some of the I/O interface, buses for the data and for the memory, and of course your I/O bus and instruction bus and so on and so forth. But the microprocessor could not function without some of the external devices that it needs. Let's say, for example, the data memory and of course your program memory. So you have to interface that to your microprocessor. Because the microprocessor doesn't have one. Also, your external I/O, so you have to connect it to the bus of the microprocessor. Now, the microprocessor evolved into the term what we call as the microcontroller, because of the need for packaging the microprocessor, the main memory or the RAM, and program memory into one device. Now, and for the purpose of controlling systems, okay, and they come up with a standard for a programmable a microcontroller that controls systems such as very not so complicated systems to control. Let's say, for example, an air conditioning unit or a cruise control of a car, and other similar devices. So you don't need a full-blown microprocessor systems for this, okay? Because it would be costly. It could be very hard to produce because you need to have several devices. You have your CPU, your memory, and so on and so forth. But with the microcontroller, with the CPU, the memory, the main memory and program memory in just one package, and it would be very, very cost-effective and very efficient as well. Now, the microcomputer, because it has changed its role from simply doing, let's say, for example, processing applications and of course computational role. The microcomputer also evolved to the microcontroller to the controller because it can control electronic and electromechanical devices. Okay, so it could control basically to rotate motor, to turn on a switch, a mechanical switch, and so on and so forth. Now, to perform the control functions, the microcomputers execute a certain program. So you have to write a program, and this program is interpreted by as an instruction to the CPU, and the CPU interprets that as a signal, or to the I/O device, or reading a signal from an I/O device. Okay. Now, the processors in embedded systems, we have the microprocessor and microcontroller. Now, we all know the microprocessor. Um, it's very powerful. Okay, and a microcontroller is not that powerful, but it could do tasks. You know, it could do tasks that is required for the particular system. Now, each of this uses a particular architecture. Okay, and that's all of them are von Neumann. But von Neumann has also a subcategory, what we call as the Harvard architecture. Okay, now the Harvard architecture, we'll discuss that more in detail later on. It's basically it's the same von Neumann machine, but the address bus and the data bus are separate. Okay, separate data bus and address bus. Okay, so solutions in embedded systems. So we have or embedded system solutions. So it's different when you have to reverse that. So embedded system solutions, including we have this ready-made systems. So we have some ARM-based SoC. So this is an example of an embedded computer. Okay, but it's not using a microcontroller. We can also use ASIC and FPGA to create system on chip. So we can design your own CPU. So you can design your own memory and RAM and ROM and put it in an FPGA, then you will now have an embedded system or an embedded computer. Okay, and usually an embedded system is attributed by some of its peripherals. Okay, because without these peripherals, an embedded system could only do very few, could only few capabilities. So we want to expand the capabilities of embedded system, particularly in communication. So we have the serial communications. We have RS-232, RS-422, RS-485. We have also the synchronous serial communications interface with I2C, SPI, SSC, and also USB cards for multimedia cards, or interface for reading such cards, and of course Ethernet, LonWorks, etc. We have also this field buses with CAN, LIN, timers, no, which is very important in an embedded system. So we have also the PLLs, phase lock loop, capture, compare. We have also discrete I/O, GPIO, analog to digital conversion, and digital to analog conversion. So we have also debugging ports such as JTAG, ISP, ICSP, BDM, BitP, and DP9 ports. So in an embedded systems, we need to, if you want to develop something, if you want to develop an embedded system, you need some kind of tools for development. So we have in-circuit debuggers. We have also software or integrated development environments such as MATLAB, Simulink, MathCAD, Mathematical Flowstone, DSP to simulate. Sometimes we use simulators, no? To simulate your design. And of course, your compilers and other, let's say, so we have software debuggers as well. So we have also your assemblers for assembly programming, and so on and so forth. And you need to have other tools if you want to explore, let's say, real-time operating systems or embedded operating systems. We also have modeling and code generating tools often used on state machines. For example, MATLAB. MATLAB is capable now of generating embedded systems codes with just creating state machines. Okay. Now, embedded systems, because embedded systems has one part of it hardware, it's also one second part of it software, and the software is categorized into architectures. So you have also simple control loop, which just you have just to run your code over and over again. We have also the interrupt control, in which the tasks are performed by the system are triggered by different kind of events. We call it interrupt sources. Okay, an interrupt can be generated, for example, let's say a timer in a predefined frequency, or by a serial port controller receiving a byte. So if there's a byte that's incoming, that interrupt is generated, and the CPU is interrupted, and it performs certain code to handle the particular interrupt. So we have also cooperative multitasking, in which each of these tasks cooperates so that none of these tasks will be delayed. So for example, a task should not go over a certain CPU time, so that the other task will not be delayed. So for example, if a task is only assigned, let's say, 5 milliseconds, then a task should perform or should be done in about 5 milliseconds. So that's cooperative multitasking. Okay, and if you want to do cooperative multitasking, so this is basically the software layers that we have to do, that we have to construct. So we have the hardware, that's basically the microcontroller and the peripherals. So we have also the device drivers on top of it. It's our codes, our piece of software that are controlling the devices, okay, and the IOs and so on and so forth. And we have the operating system to manage the task, to make sure that none of the task is delayed, to make sure that the task performs at its prescribed CPU time, okay, or its completion time. And of course, we have this microkernels and exokernels. These are kernels from a desktop operating system, and it's converted into an operating system that can run an embedded system. Okay. We have also monolithic kernels, such as Linux or Windows or Android. Those are what we call as monolithic systems. Add to that, we have also iOS and BlackBerry OS. We have also Firefox OS and all of this stuff that runs that can run an embedded system. We call it monolithic kernel. Of course, monolithic kernels is very powerful. You can handle multimedia, multitasking. It could handle almost every communications, GSM, LTE, and so on and so forth. No? So, of course, you need to have a special hardware for that. You can handle such very powerful tasks. Okay. Now, the microcontrollers, in other hand, that we are going to use as our platform for embedded systems. Okay, so these are developed because we need to have alternatives to microprocessor. It's very expensive. The microprocessor itself is very expensive, and if you want to only control, let's say for example, a few tasks, and if you use a let's say a 32-bit microcontroller, a microprocessor, it will be very expensive. It's just a microprocessor alone, but you have to have the memory and I/O controller and so on and so forth. Okay, now a microcontroller is basically a chip. It's standalone system. It's built in RAM, ROM, EEPROM, clock generators, whatever you need to create an entire computer system. Okay? And then we discuss more about microcontrollers in the next chapter. Alright? So, before we start with microcontrollers, as a bring home experience for all of you, I would like first, I asked earlier, that think of applications and embedded systems. Okay, I want also for you to study in advance about microcontrollers. What are these beasts? Okay, what are these? What are microcontrollers? Know more about them. Know more about who are manufacturing microcontrollers. What architecture are they using? Features and so on and so forth. What are the commonalities of the microcontrollers? And we will discuss that, your findings, on the next meeting. Okay, so that's all. Thank you very much for listening, and see you all next meeting.